Hello everyone and welcome back to the Data Structures and Algorithms course. The topic for today's lecture is Huffman Coding. So what is Huffman Coding? So Huffman Coding is an algorithm which is used to compress our data. So using Huffman Coding, we have something called as Huffman codes, which we can create, and using these Huffman codes, we we assign some values to our already given information to somehow compress it so that it takes less space. So just like how we have zip files, which are used to compress big files into smaller sizes files, we have Huffman coding. So the basic idea for that is for each character we know it takes 1 byte of storage. So 1 byte equals to 8 bits. So each character takes 8 bit of storage if we had stored it as a character. But instead of storing it as a single character, we will store it in form of smaller sizes. So we will instead store the more frequently occurring characters using fewer bits and less frequently occurring characters using more bits. So the basic idea is that although yeah, although they are all characters, we will observe that some characters occur more often than some other characters. So if you try to give if you try to make these more frequently occurring characters have take up less space, and and then the scarcely available scarcely frequent characters, if we assign them large spaces, then on average our total size would be decreasing. So on average, this should decrease the file size by usually half. So we look into it how we can do so. So here's an example. So let's say we have a string called Duke Blue Devils. So what we have to do first is we have to count the frequency of each character which is occurring in this string. So if we count everything, we can say that E occurs 3 times. We say D occurs 2 times, U occurs 2 times, L occurs 2 times, the space character occurs 2 times. Similarly, K, B, V, I, and S, these all occur 1 time. So what we want to do is we want to make E, since E occurs the most, we want E to take up as little space as possible, such that instead of, yeah, we want to make E take as little space as possible. Uh, So what we have to do is we are assigning these nodes like this. So each node has the character for what we are assigning and the value we are assigning, and the value is the frequency of the count. So this node has E and 3. Similarly, for every other characters we assign, we make these nodes. So we will now create a tree out of them. So let's show the example. So here what we have to do is we take up any two nodes with the smallest frequency. So in this case, with these two have the smallest frequency, which are 1. So in this case, we are taking these two, but we can have taken, let's say, V and I or K and S. So we could have taken any two. So we take any one pairing. So here we are taking I and S. So we combine them. So how do we combine them? We make these two children node of a single internal node, and we assign that internal node the value 2. How did that 2 came up? It came up by adding these two frequencies. So this was 1 and this was 1. So we added up 1 and 1. We got 2. And we made this tree with the 2 as the parent and INS as its children. So now again, from all these nodes, we'll take the nodes with the two smallest frequencies. So here we are taking B and V. So if we combine them again, we get this. So we have 2 as the parent, and then we have B and V as its children. So from this remaining, now we take the two smallest. So we have one occurrence of one frequency, and then we have multiple occurrences of two frequencies. So we take any of these two frequencies. So in this example, we are taking this two frequency. So 1 and 2. So we will combine these two now. So it combines something like this. So again, and the K1 becomes one child, and this tree becomes the right child. And the total and the internal node value is 3 now because 1 plus 2. And here we got 3. So next to the two smallest here, we are taking 2 and 2. So we combine these two, we get 4 as the value of internal node. And then again, we are taking D and U. So 2 and 2, it adds up to 4. And now we have these cases. So now we have to take the two smallest. So we have a 2 and we have two occurrences of 3. So we could have taken E3 or we could have taken this 3. So in this example, we are taking this 3. So now we can combine these two together. So the value here would be 5, as 2 plus 3 is 5, and then 1 is assigned the left child and the right child is the other one. So from these remaining top nodes, 3 and 4 are the smallest, so we combine these two, value becomes 7, then 4 and 5 are the smallest, value becomes 9, and then finally 7 and 9 are the two remaining, so we finally combine them, and in total we have this tree with 16 total frequencies. So if we count up the entire string, we see that we have 16 characters including spaces. So 3 plus 2 plus 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 1 plus 1, it adds up to 16. So basically we have made up this tree, and as you can see, what you will observe is that the uh, the characters which have a much larger frequency occurs higher up in the tree. So we see that E is the character which had the high frequency, which was 3. So you can see that the leaf node of E3 is at height 1 to 3, which is very near to the root, and the other and as we go down, the frequency decreases. So here we have at height level 4, we have frequencies 2, and at height level 5 and 6, we have frequencies 1. So what we have done is somehow made the tree in which better higher the frequency, higher up in the tree. Sorry, it is nearer to the root, the leaf node. So we will somehow use this to uh, make a special code for each characters, and such that we can use that to compress the files. So what we have to do is we assign in the tree with values and assign codes to the tree by placing a 0 on every left branch and a 1 on every right branch. So if we go left, we assign it the value 0. If we go right, we assign it the value 1. We will look into it. So a traversal of a tree from root to the leaf node gives us the Huffman code for the particular leaf character. So for the character L, what we have to do is we go to the right, then we go to the left, and then we go to the left. So for the according to our values assigned, so left was 0 and right was 1, so it would be 1 since we're going right, then it would be 0 since we're going left, and then 0 again because we're going left again. So the code for L would be 1 0 0. So here is the assignment of each codes. So as you can see, for E it would be 0 0, and then for D 0 1 0, and everything up until V, which was 1 1 1 1 1. So these are all the leaf nodes. So as you can clearly see, what we get is that the character which had the highest frequency, which was E, takes up the least amount of bits. So E only takes up 2 bits, whereas the others which had one frequency takes up much larger amount of bits. So V has 5 bits, B has 5 bits. So and the ones which had 2 frequency, which was in the middle, has in between number of bits. So in this case, we are having 3 bits. So if we use these codes uh, to assign these characters, we'll see here. So we have blue devils. For each character, we assign it that value. So for D, we had value 0 1 0. So we assign the value 0 1 0. Then comes U. So U has value 0 1 1. So we assign it next 0 1 1. Then for K we had 1 1 1 0. So we assign it 1 1 1 0. Then for E we had 0 0. Then for space, keep in mind we have to take space into consideration. So space had 1 0 1. Then B had 4 ones and a single 0. So in this way, we convert all of these characters into its bit form according to this tree, the tree we created. So keep in mind that this tree could be different according to what nodes we, according to how we create this tree. So like here we could have taken 3 and 4, sorry, this 3 and this 4 to make the common tree, and in that case the tree would look a little bit different. So each of these would have, and these characters would have somewhat different values. But in total, what the thing we observe is that the total length, or the total number of bits, sorry, total number of bits required is, you can see here. And so it, how many is it? It is 56 minus 4, so it is 52 bits in total. So if we convert it into bytes again, so we have to take it in groups of 8. So if we assign it in groups of 8, we observe that it takes up a total of 7 bytes, which is clearly less than 16 bytes if we had taken it character by character, since each character was 1 byte. So in this way, by assigning them these bit values and making the most highly occurring characters and assigning it the smallest number of bits, so we see that since E comes up most, we are assigning it the least value. So it only takes up 2 spaces here, 2 spaces here, 2 spaces here. Say, let's say if E took up five bits, then it would be counted 5 in 3 different places. So it would basically increase it by 3 into 3. So it would increase it by 9 bits. So to decrease the total number of bits required, the most highly free occurring character is assigned the least number of bits. So here you can see that it almost like it more than half the total amount of bytes required. So 16 bytes was uncompressed, and after compressing using Huffman coding, only 7 bytes of space is required. So this is how we did compressing. So to uncompress, so uncompress the file back to its original form. So what do we have to do is we have to read the file bit by bit. So this was a bit to bit representation. Here 0 1 0 0 and then 4 times 1 and then followed by everything else. So we read it bit by bit. So first we took 0, then 1, then 0 0. So we start at the root of the tree. So root of the tree was here 16. We start here, and then we go, if a 0 is read, then we go to the left subtree. If 1 is read, then we go to the right subtree. And then when a leaf node is reached, decode that character and start over again at the root of the tree. So we know that from this tree, every character that we had occurs as a leaf node, and every other internal node, it's just the total sum. So we do not need these. So whenever we encounter a leaf node, we know that it is for that character. So uh, we can decode that character, and then we can start again for the next character. So let's say if you try to go back, if you try to decode it, so we encounter a 0 first. So from the root we encounter 0, we go to the left. Then we encounter a 1, we go to the right. We come here to 4. Then we encounter a 0. And from 0 we get to D2. And we know that this is a leaf node since it has no children. So we can say that we can we can decode that the that the character was D in this case. So we get D, and then we come back to the root node, and then we start for the next. So after 0 we had again 0. So we go to left, then we had uh, double 1. So sorry, we had double 1. So we go to the right and then go right. So we can say that the next character is U. So in this way we can do bit by bit, and whenever we encounter a leaf node, we know that that is the decoded character, and then we start back from the root of the node up until the last, which was 1101 here, which will give out something around S. So that is how we will decode it. So thus we have to save the Huffman table information. So this code is exclusive to this type of tree only. So since we decoded it using this tree, we have to store this tree for decoding. So we cannot just have another type of tree and which had different values of bits and get the same decoding, of course. So we have to store this table somehow. So for that, we generally use a header file, and it takes up a little bit of space, but it does not take that much. And it is fully worth the compression. So it doesn't add a significant amount of size to the file for larger files. And since compression is done for only larger files, it is really insignificant. So, or either you use this, in which we had created a tree of our own. Here we created a tree of our own. What we could do is we could use a fixed universal set of codes and frequencies. So there are universally accepted Huffman trees. So using those, if we use those codes of those to encode our message, then we can just use that uh, same table to decode. So in that case, the information is uniform, and we don't have to pass on each table every time. If we set aside that, if we follow that universal set of codes. So that was Huffman coding. So we learned how to compress this string into smaller size using bits and Huffman tree. So that was it for today's lecture. In the next lecture, we will start to look at graphs, and see you in the next lecture. So goodbye.